We are still in chapter 19. In the last slide, we introduced the torque on a coil, on a current loop. If you keep that in a magnetic field, it will experience rotation, right, because of the magnetic torque. So this has a great application, mainly converting the electrical energy to mechanical energy. How do you get a motor? So electric motor. An electric motor converts electrical energy to mechanical energy. So what happens is just we take a current carrying loop. We can connect this loop, what I have in my hand here. So you have seen this before. You keep it in a magnetic field between the big magnet, and it will start rotating. So we have a motor, right? That's what we need, a motor that will. Right. So we start with the DC motor, meaning the power supply is a battery that sends a direct current. The problem with that is, when it will have a torque with the magnetic field, applying the right hand rule, it will rotate it. And when it comes to this position, vertical position, there'll be no torque. But however, because of the already has got some velocity, it will, because of inertia, it will go past the vertical position. But when it go past the vertical position, if it's the same direction of the current, you can again apply the right-hand rule. You see, the torque will be in the opposite direction. It will start rotating, it will try to get in the other direction. Then it will be in the other direction. Then it will end up stopping at the vertical position. If you keep it like this, it will have a torque. From your perspective, it is clockwise. When it passes the vertical position, there will be a counterclockwise torque. So it will move this way, then clockwise, it will move that way, then it will stop in the position, vertical position. It will not be a motor, right? It will not be a motor because, well, if you keep it like that, it will come, then go like that, and it will stop in the vertical position. So when you have a DC voltage applied, we have a solution. That is, if you can see this diagram here, this coil is connected to a battery via brushes, and they have what is called split ring commutators. If you look at it, it is two rings split in the middle, one ring split in the middle. So you have a half ring above, half ring below. So the brush from the positive terminal of the battery will be touching the upper ring, say at one point. And as this thing, the split ring is attached to the coil, right? So it will be rotating with the coil, the split ring as well. So, but this DC motor is stationary and the brush is also stationary. So it is touching the upper ring. When it comes to the vertical position, it will be between the gap between the two rings. You don't need to send current when it's in the vertical position anyway, because there is no torque. Vertical position theta equal to 0. That means perpendicular to the ring and the magnetic field in the same direction. Theta equals no torque. Even if there is current, there is no use. So then what happened, as it turned to the other side, this brush will be touching the other ring. And therefore, the current direction will reverse. Before the current through this is going like that, and when it is touching the other ring, the current direction, after it passes the vertical position, the current direction will be opposite. It will be towards you. That will make the torque not counterclockwise, again clockwise. So it will continue to rotate. So this mechanism of split ring commutator will make the torque to be, in this example, clockwise continuously. So the loop will not stop, it will continue moving. And again, the same thing will happen at this point, if you don't have the commutator, again, it will not change the direction, so it will stop there. But we have the commutator, the current direction will therefore change, and it will keep rotating in the same direction. So we have a smoothly operating electric motor. So I can show you with some simple animation in YouTube video. So I have already opened it. So let me go to that. Yeah, this one. So here you see the commutator very clearly. So it is nice animation. So what happens now, there will be a torque, it will rotate. So the magnetic field, well, the direction of the north-south is different, but it doesn't matter. We also change the direction of the battery. And now what happened? So it has, from your point of view, you have a clockwise rotation. And see what happened. The brush is touching one of the ring, say the left side ring. So as it comes to this position, it is exactly when it is vertical, it is not touching either of the ring. It was touching this ring, right? So the current direction will be on this into the board. Okay, right. Now when I am at this position, when it is vertical, okay, let me bring it vertical. It is not, it has stopped touching this upper ring. Now it is going to touch this one. Okay, as I move, it is going to, not yet. Okay, because there is a lot of sound audio here. So that is why it is not moving. Well, let me pull more. Right, see, it is touching the lower ring. That makes the current direction to change. If you don't have this mechanism, the current direction will not change. Okay. Now, when you make the current direction to change, again, the torque will be clockwise from your point of view. It will be still, again, it will make it clockwise. Making the current direction to change will result in the torque to be, or the rotation to be clockwise. So we will have a continuous rotation of this coil, right? And so that's, I want to bring this to show it to you three-dimensionally, so you understand the function of this commutator, split ring commutator. It is called the commutator. Now, coming back to this, let me start this again. So I have the, right. So this is the motor. So we are done with the slide. We also showed you the animation, the link. So this explanation again, but let me read through that. Whatever I said before, it is repeated here. An electric motor consists of rigid current carrying loop. The current carrying loop is solid, rigid, and it is placed in a magnetic field. The torque acting on the loop will try to rotate it. In this our case, it was a clockwise rotation. But when it comes to the vertical position, when theta equal to 0, you know what is theta? Theta is the perpendicular to the plane direction and the magnetic field direction. So when it is vertical, it is theta equal to 0. When theta equal to 0, you don't have a torque. You know the equation. You remember the equation, sine 0. Theta is 0, sine 0 is 0. So we have a 0 torque. If the loop turn past this point and the current remain in the same direction, the torque will reverse. It will now rotate in the opposite direction. So then you will have, no electric motor. There will be a motion, then it will stop in the vertical position. So to provide the continuous rotation in one direction, what we have this trick with the split ring commutator. So we need to reverse the direction of the current. We achieve it through this split ring commutator. If you use the AC supply, then we have AC motors, and we are not discussing it now. The reversal occurs naturally in an AC current. In every half the cycle, there's a reversal of the current, so it happens naturally. Then you don't need such a split ring commutator. But in DC motors, we use this mechanism of split ring commutator, like I explained you. Every half the cycle, the direction of the current reverses, therefore it will keep rotating in the same direction. In an actual motors, we will have not just one loop, but many current loops, and also not just one commutators, there'll be many commutators around this magnet. So that's a commercially, that's how you get, smoother rotation. So keep explaining what I said before in so many words. Yes, just as the loops become perpendicular to the magnetic field, the torque becomes zero, but the inertia will carry the loop forward, okay? Although the torque is zero, because it had some velocity, it will continue to go to the right side of the vertical position. And the brushes cross the gap in the ring and it will touch the other side of the ring, that will reverse the direction of the current. So you'll have a continuous rotation in the same direction. We have another link. This one, I'm not going to show you, but please do it on your own. If you click this, you can see how you can build a motor on your own with some batteries, this 1.5 volt battery and some copper coil. You can create a battery on your own, right? Build your own motor. Now, we come to the next section, Ampere's law. So that's a law that tells you how to get the magnetic field from current carrying wire. So that is Ampere's law. But before we come to Ampere, we have to talk about another person whose name is Ørsted, Hans Christian Ørsted, known by Ørsted. He is known for observing a compass needle. He bring a compass needle. Now what happened? Compass needle will show if there is a magnetic field. Of course, there is always a magnetic field from the Earth. So it will be pointing in a certain direction, in the direction of the Earth's magnetic field or any other magnets that are around. So when you brought it near a wire, which is electric circuit, and there's a current in that wire, when you bring it near that, it deflects. So it is changing, it's showing there is another magnetic field. So current carrying wire actually produce magnetic field around this wire. So that's what the compass needle was detecting. It was an accidental discovery. So he's the person. Ørsted is the one who discovered it first. The first evidence of connection between electric and magnetic phenomena done by Ørsted. He saw that a compass needle would deflect when placed near a wire carrying a current. And he did many experiments. He figured out, suppose there is a wire, say this is the wire that carries a current, say in this direction, upward. And you, in the plane perpendicular to this wire, maybe keep a cardboard, something like that, and you place many compasses around it, you will see that there is a magnetic field because the compass needle will deflect in the direction of the magnetic field. And this magnetic field have a field line circular around this current carrying wire. So any current carrying wire will have a magnetic field around the wire in a circular magnetic field lines. So magnetic field line tells you the direction of the magnetic field as tangent to that line. And the compass needle will point in whether it is one way or the other way, the tangent. Okay, so this is you know that when there is a current that flows in a wire, there will be magnetic field lines, magnetic field created by this current, which will form a circular magnetic field line around this wire. What about that circle is pointing clockwise or counterclockwise? That also, we know how it is. We use a rule called right-hand rule number 2. So now you should not confuse the right-hand rule number 1, that is for the direction of the magnetic force. Right-hand number 2 is for the direction of the magnetic field line from current. What you do, again, you take your right hand, grasps the wire, so your thumb is in the direction of the current. So it's the opposite way. You use the thumb to point it in the direction of the current. You only use the right hand, and the curling of the finger will tell you whether it is clockwise or counterclockwise. So here in this case, the current is going up, and you use the right hand or the left hand, and you're curling it, and your thumb is curling, your fingers are called curling. Thumb is pointing in the direction of the current, and the fingers are curling counterclockwise. So that tells you what should be the direction of the magnetic field. So please don't confuse these two direction rule. One is for magnetic force direction, one is for getting the direction of the magnetic field line when there is a current carrying wire. Then experimentally, they figured out the magnetic field from a current carrying wire, a long current carrying wire, a distance r from the wire. Say at this point, if someone asks you, what is the magnetic field at this point P? And it is equal to mu0, a constant. It is proportional to the current that is going through the wire, obviously, more current means more field. And it is inversely proportional to the distance. So if you move away from the wire, the magnetic field will reduce, it will become weaker. So it is 1 over r relationship. When you come closer to the wire, it will increase. And plus there is another constant 2 pi below. So this is an experimentally verified equation. And the value of the mu0 is this much, 4 pi into 10 to the minus 7. Okay, so this mu0, it denoted in terms of the Greek letter mu, is called the permeability of free space. Maybe you remember in electricity we had this, epsilon 0. That is called the permittivity of free space. Free space here means vacuum or air. So there's not much difference between the mu for vacuum and the mu for air. So we just use the mu0 here. Do you have to memorize this? Not really. Okay, it will be given in the formula sheet. Like this value will also be given in the formula sheet when you solve question on electric field. Now comes this ampere. So this section topic is Ampere's law. So Ampere is the one who provided theoretical basis for finding the magnetic field from a current carrying wire. If there is a current, how do I get the magnetic field? So he gave the theoretical basis for that. So the law is called the Ampere's law. He is credited with the discovery of electromagnetism. Okay, so combining the electric and magnetic field together, the relationship between electric currents and the magnetic field. Ampere found a procedure for deriving the relationship between the current in an arbitrarily shaped wire. Let's say we have a wire like this, okay, not necessarily a straight line, okay, let's say a arbitrarily shaped wire. And let's say through this wire, there is a current I flowing. Let me use red color for this wire, okay, fine. So say there is a wire, and it is some arbitrary shape, not a straight line, and the current through the wire is I. Then he said, fine, what you do now, you imagine a circuital path. Circuital means a path which start from a place and go through a line and come back to the same place, closed path, a circuital path. So let me imagine a path. So let's say I'm coming, this is out of the board. Okay, right. So this circuital path, the green path, maybe it's a circle, doesn't have to be a perfect circle. It can be any shape, actually. It can be any shape, but it has to be a closed path. So imagine a closed path like this that encloses this current. Then you calculate this one. We want to say there is a magnetic field from this wire, current carrying wire, and we take a small section delta L of this circuital path, and let's say the magnetic field parallel to this delta L is B parallel, and you take this product B parallel into delta L, and we do this for all the segments. We break it into small delta L in this along this path, and you move in a certain direction. Start from point A and move along this path, the green path, and come back to the same point, complete the circuit. And while you do that, combine, take this product and add them all. Sigma mean sum, right? Add them all, and it is equal to mu0 multiplied by the current I through the wire. This is the Ampere's law, Ampere's circuital law, because you apply it on a circuit. Okay, it says a cycle, a closed path. So it is called the Ampere's circuital law. The sum over the closed path, okay, it has to be a closed path, is equal to the constant mu0 multiplied by the current. And this current has to be given with the correct sign, positive or negative. How do you get that? It depends on which direction the path is taking. Suppose you are moving, looking from above, if you are moving counterclockwise, then curl your fingers in a right hand, and you curl your fingers counterclockwise. The thumb is pointing up, so up will be positive, down will be negative. That's how you assign the sign for I. So you should put the I with the correct sign. That depends on how you go around this path. If you go around the path counterclockwise, up will be positive, and the other direction will be negative. Can you go around the path clockwise? Yes, you can do it, but then the current will be negative. If it is up, it will be negative. If it is down, it will be positive. So you have to correspond it with how you are traversing the path. So here again, it is much clearer than my diagram. So let's say the wire is not arbitrary shape. Say it is a straight line here. It depends on how you take it. Yeah, not all. It depends. Suppose you are going like this. You are going this way, right? So you curl your finger in the direction of your moving, then thumb is pointing up. If when you go like this, up current is positive, down current is negative. But suppose you decided to move in this direction, right? Then the right hand show you the down is the positive. In that case, you have to take the down to be positive and the up is negative. So depending on how you are moving in the circuital path, okay, it is up to you. Okay, it is up to you. So you have to stick to what you have done. You should be aware of how you did that. Then you get the sign accordingly. Then you get this for each segment delta L and add them all, and you say it is equal to mu0 into I. Right, now let's apply the Ampere's law for long straight wire. A long straight wire. We already have the expression, right? We saw this is how we said, experimentally we can prove that. Now, can I derive this expression by applying the Ampere's law for a long straight wire carrying a current I? Let's do it. So let's imagine there is a long straight wire and it is carrying the current upward. what do? You choose, imagine a circuital path. Let that path be a perfect circle with the center at the wire. And let's say the radius of that circle is r. So, and from symmetry, we can say the magnetic field must be the same everywhere on this circle, must be a constant, because there is no other way, because we are talking about an infinitely long wire. So the magnetic field, there is no reason why the magnetic field will be different along this circular path. It has to be constant. And also one can show that it must be tangent to that circle. Okay, so I'm not going to discuss it now, but you have to take my word for it. The magnetic field must be tangent to the circle. And let's say I start from this point P and go counterclockwise and come back to the, so I decided to go counterclockwise. And so we already know from our right hand rule number 2, the magnetic field, because I put the thumb in the direction of the current, and the magnetic field will also be in the counterclockwise direction. So at this point, let's say we take a small delta L, and the magnetic field is B. So you can apply the Ampere's law. It is, what is Ampere's law? Is equal to mu 0 I. And you have to collect all these and go around this circuital path, which is a circle now. We know this is a constant. The B is a constant. It is the same everywhere along the circle. So I can take it out. The sum of all the length is equal to mu 0 I. This is what? This is the length of this circle. What is the length of the circle? Circumference, right? It's called the circumference. Circumference of a circle is given by the formula 2 pi r. So B multiplied by 2 pi r is equal to, so r is small r, right? So that's equal to mu 0, the current enclosed by this circuital path. There is a current which is I, right? And since I was going around in a counterclockwise path, up will be positive. So my current is also up. Therefore, I'll put positive I. So now we can take it to this side. B is equal to mu 0 I divided by 2 pi r. So we got the same relationship that we had for the long straight wire before. So we are proving that using Ampere's law. Okay, now we can do an example question, but this time we have 2 wires actually, not just 1 wire. What are these 2 wire? Coaxial cable. I don't know whether you know this coaxial cable. Any cable that you have, like what you plug in for the USB cable, or that's a coaxial cable. Okay, USB cable has many wires, but simple wire like I don't know. Before they used to have this from the antenna to catch the signal. There is a coaxial cable. Anyway, coaxial cable actually like this. We have 2 wires. One wire is in the middle, and there will be a current. If you want to connect a battery to a bulb, you need 2 wires, right? One from the positive terminal of the battery, one from the negative terminal of the battery. The positive terminal will go to the bulb and come out. So you can use a coaxial cable. It looks like just 1 wire. It is actually not. It has 2 wires, one in the middle, which is carry the current, let's say, to the bulb. And from out of the bulb, it will go to the outer sheath. See, this is another wire. This is 1 wire. What is in the middle is 1 wire that carries the current, let's say, from the positive terminal of the battery. And it goes to the bulb. let's say it goes to the bulb, and from the bulb comes out, and now this time to the negative of the battery through the outer sheath. Okay, it is not just one piece, it is outer sheath, the whole like a skin. So it comes out. You probably, if you have, if you tear it apart, you will see there's a wire mesh here. So the current will flow through. So the direction of the current will be in the opposite direction. In the middle wire, if it goes up, from the outer wire, the current will flow down. So it actually two wires in one cable. So it's called the coaxial cable. Right. Now the question is, calculate the magnetic field inside the cylindrical conductor. So you call it. So where somewhere here between the middle wire and the outer sheath, somewhere here, when the value is 0.5 centimeter, it is something in between the two wires. At that point, what is the magnetic field? So to answer this question, we imagine a circuital path, a circle, say this green line of radius 0.5 centimeters, and we do the same thing like before. This is the Ampere's law. And we say that B is a constant because of symmetry. I can take it out. Then we have the total length, which is the circumference, is equal to mu0, and the current inside this green circular path. The current inside that green circular path will be only the current I1, right? Because I2 is outside that green circular path. So what you should have here, total current, but the only current for that green circular path, only I1. And it is the same because I have chosen to move counterclockwise. That will make the up to be positive, and I1 is also up. So I should put plus I1. Then you do that, you get this expression for the magnetic field at a point between the two wires, out of the first wire and below the second wire. So only I1. So you substitute I1 equal to 3 plus 3, and you substitute for R 0.5 centimeter. So centimeter made into meter will be 0.005 divided by 100. You get this answer for the magnetic field. Done. Part B. Now calculate the magnetic field at a point which is out of the whole wire, something like this, which is 1.5 centimeter. It is greater than the diameter of the whole coaxial cable. So then you need to get another circuital path. Let me use the red pen. So now this diameter is, the radius of this path is 1.5 centimeters. Now this circuital path is going to include both I1 and I2. Again, we apply the Ampere's law, which is this. This time we can again tell it is the same magnetic field, it's a constant, so I can take it out of the summation. So it will be that magnetic field multiplied by the circumference of the red circle, which is 2 pi r, radius of the red circle, equals mu0, that is the right side of the Ampere's law, multiplied by the current enclosed by this big circle. Now this time, this circle enclosed both current, I1 as well as I2. But you have to be careful here. I1 is positive because we are going counterclockwise. That will make the up direction to be the positive direction. So I1 is positive. I2, if it's the magnitude, I have to put minus sign because it is going down. Because I choose the clockwise to be my direction to go around, that will make the up direction to be the positive direction, the down direction to be the negative direction. So I1 you will put plus 3, I2 will put minus 1. And then you just calculate the answer. So why let me repeat, okay? Right, this is the Ampere's law. This is the Ampere's law. I has to be substituted with the correct sign. How do you know the sign? So I'm coming to that part. Okay, this should include all the currents in that circuital path. So red is our. I'll go to the second part B question. Red include both current, right? Inside the red circuital path, we have current I1 as well as current I2. Okay. Now that means I1 will have some sign. If it is positive, I2 will be negative. It's in the opposite direction. How do I decide which one is positive, which one is negative? Okay, I'm coming to that. So you are, let's say, when you want to do this, when you want to get this, it's a closed path. You need to decide on a direction. Are you going to go clockwise or are you going to go counterclockwise? You tell me, how do you want to go? It's up to you. Say you want to go clockwise. Okay, good. Let's say you decided, here he is going counterclockwise, right? You decided to go clockwise. If you decided to go clockwise, down will be, no, positive, yes. Down will be positive and up will be negative. Don't change now, okay? So you decide. So anything down will be positive, anything up will be negative because you find. So the direction of B, you know, from our right-hand rule, we don't know actually. We don't know what the direction of B. So this, we are going this way. So B, the direction, you don't know. So this, you are decided to go this way, and this direction is a positive direction for me because you're going that way, and the other direction will be negative. Imagine you don't know which direction it is. You know it is tangent. So let's say I thought it is this direction, same direction as I am going. We don't know. We have to find out at the end. Let's say it is this direction. So you will say B and delta L, they are both in the same direction because I'm going this way, and the summation is equal to mu 0, I is the current enclosed. Now we can say this is constant, so I will take it out. And sigma delta L mean circumference, right? Sigma delta L mean the total length of the red circuital path. So it is the circumference. So it is 2 pi r equals mu 0, the current inside this with the correct sign. Since I am going this way, down will be positive, up will be negative. So the I1 will be negative. I1 is the magnitude side, and I2 will be positive because you decided to go clockwise. What do you get finally? B is equal to, you know, I'm getting B is in this direction with the magnitude of so you are saying B is in this direction with the magnitude of that. Suppose you decided to go the other way direction, you will get B is equal to this one, right? So for this, you're getting a positive value. When you say the magnetic field is this direction, you will get a negative value. Both are the same. Both are the same, right? Because you are getting a negative value, then you conclude what? My direction is not correct. Actually, the magnetic field is in the other direction. Okay. Right. Now we come to another section or subtopic: magnetic force between two parallel conductors. Imagine you have two wires, they are conductors, wire 1 and wire 2. So wire 1 carries a current I1, and wire 2 also carries a current I2, and they are kept parallel to each other. Okay, parallel to each other. The distance between them is d, one distance, and they are in the same direction. Let's imagine same direction. Then we'll take the case when they are in the opposite direction later. Let's say they're in the same direction, they are parallel to each other. One is carrying a current I1, the other one is carrying I2. Right. You learned before, if you keep a current carrying wire in a magnetic field, it will experience a force. That's what you learned before. If you have a current carrying wire, if you keep it in a magnetic field, it will experience a magnetic force. We learned that before. So this wire number 2, now also we know now, if you have a wire, it is like a magnet. It will have its own magnetic field. So the wire number 2 is like a magnet now for wire number 1. And from this, we just learned it. It will have a current at the, it will have a magnetic field from wire number 1 around this wire from wire number 2 is carrying a current. So it is like a magnet. Around this wire number 2, there will be magnetic field. And at the point where wire number 1 is, let's say it will have a magnetic field B2. Okay, you know how to get the direction. Put your thumb in the direction of the current, and at this point there will be a magnetic field B2 acting on the wire number 1. So wire number 1 is carrying a current, say in that direction, and perpendicular to that, because you know it will be perpendicular out of the board, there will be a magnetic field acting on the wire perpendicular to the current I1. Then you learned at the beginning of the chapter, if there is a wire that current carrying wire kept in a magnetic field B2, it will experience a I L cross B. It will experience a magnetic force given by this. So the magnitude will be B2 is the magnetic field, L the length of the wire, and current is I1 through the wire number 1 into sine theta. Where did the sine theta go? Why don't we see the sine theta? Theta is equal to 90. Sine 90 is 1. Okay, not cosine. This is the I direction. This is the B direction. I and B are perpendicular. Sine 90 is 1. So this is 1. That is why it is not there. Okay, you don't have to put it. So the force on wire number 1 is magnetic field coming from wire number 2 multiplied by the length of the wire multiplied by the current through the wire 1. So now for B2, we just learned magnetic field from a current carrying wire is given by mu 0, the current through the wire, which is the wire number 2, divided by 2 pi d. This is the distance from wire 2 to wire 1. So we substitute for that. Then finally we get this expression for the force. I brought this L to this side. So force per unit length, force divided by the length is equal to mu 0, I1, I2, 2 pi d. So we got, yeah. Again, right. So these are the two wires. So this is wire number 1. Okay, this is wire number 1. This is wire number 2. They are kept parallel. So from this wire, there will be a magnetic force, magnetic field at this point. How do you get this? Like this. So it will be like this. The direction will be like this. This is I1. This is B. So the angle between I and B is the theta, which is 90. Sine 90 is 1. Okay. See, this is like a magnet now. This guy is like a magnet. This guy will apply a magnetic field on wire 1 in this direction. So this is the current direction. This is the magnetic field direction. They are perpendicular to each other. So sine 90, sine 90 is 1. I answered you. Okay. So anyway, at the end we get this equation. So this is what is important for you now. What is this equation for? When you have two wires kept parallel to each other, and wire number 1 has a current I1, wire number 2 has a current I2, and there'll be a force on 2 on 1, and this is the formula for that force. We can do the same thing for the wire number 2. Now you can say the wire number 2 is carrying a current in a magnetic field created by wire number 1. And you will get exactly the same equation. So wire number 1 will experience a force from the magnetic field because of the magnetic field from wire number 2. This is the equation. And similarly, wire number 2 will experience a magnetic force from wire number 1 because of the magnetic field created by wire number 1. And you will get exactly the same equation. Right? So this means when you have two wires kept parallel to each other, they will exert force on each other given by this magnitude. If the current is in the same direction, the force will be attractive towards each other. If the current is in the opposite direction, the force will be repelling, pushing each other away. So that's the summary, okay? So you don't have to worry too much if you cannot follow the proof, no problem. Just this equation. So you should know where this equation is applied. When we have two wires carrying current I1 and I2, they will exert force on each other. The magnitude of the force per unit length, is given by this equation. And what else you have to remember? The direction. If they are in the same direction, the current is in the same direction, it will be attractive force towards each other. If they are in the opposite direction, it will be repulsive force, so away from each other. Right, now we can use this magnetic force between two parallel wires to define the SI unit for current. So let me rewrite the equation. What is the equation? Force per unit length is equal to mu0 I1 I2 divided by 2 pi d. This is our equation. So we do this experiment in this way. To take two parallel wires and make this d equal to 1. So keep them 1 meter apart. So d is equal to 1. Then you send the same current through both of them. So there is no need to put I1, I2. I can call it I squared because both are I. So I will call it I squared. So that's important. Carry the same current. So, and you adjust this current, keep it the same. It's very easy to do. Adjust this value of the current such that this is equal to 2 into 10 to the power minus 7 Newton per meter. Right? So we adjust the current until the force can be measured. The force between them is very small force, okay, per meter. Okay. Then I can show you I squared is equal to 1. Let me show you how. The left-hand side is 2 into 10 to the minus 7. Mu0 is 4 pi into 10 to the minus 7. I squared 2 pi, and d is equal to 1. Now look, 2 pi cancel with 4 pi, you'll have a 2. 2 will cancel with this 2. 10 to the minus 7 will cancel with 2. So I squared is equal to 1. Okay. So that's how we define the SI unit for current, and we call it ampere. 1 ampere is what? You know how to get the 1 ampere. You take two wires, make sure you have the same current through both of them, make the distance between them 1 meter, and adjust the current until the force per unit length become this much. Then I know the current is 1 unit, that we call it 1 ampere. That's how you define the ampere. Then after defining the ampere, you can define the coulomb. It's also electricity unit, the amount of charge. So because what is the definition of the current? Yeah. So when, if a conductor, you know how to get the 1 ampere. Make the current equal to 1 ampere, and then the quantity of the charge that flows through this cross section in 1 second is 1 coulomb. Right, now we got to the next section. Maybe I'll make this another one, but we'll stop with this. It will take some time as well. So if you have a long straight wire, you know at a distance r, the magnetic field is equal to mu0 I over 2 pi r. Fine. Now we take this wire and make it into a loop, okay, circular loop. Now I can say, if you take a small portion here, delta x, because of this current here, okay, current is flowing this way, at the center of that circle, we have a small current dB. And another one, there'll be another dB. So what happens from each segment, I can show the current at the center is upward, okay? And this will, each segment contribute and increase the strength, and you will have a final magnetic field, say B1. So can I get an expression for B1 at the center? It is easy to do it, but okay, it will be done later, okay? So my point is, you can take a straight wire and make it into a cycle, and thereby we can get a strong magnetic field at the center of that circular loop, and it will be upward if the direction is counterclockwise. And if I draw the magnetic field at the center, it will be upward like that, and you know, a little bit to the either side of the center, it will become a little bit turned, and when it come closer to the loop, it will be a circle like that. So what does it remind you? A bar magnet, right? So if you have a bar magnet, this wire, this loop is like a magnet, a small magnet. So if you have a current that flows in a circle like that, it is actually a magnet. So by curling your finger, you will know which side is north and which side is south. And we can have more than one loop. Right? Now this is a magnet, right? You can have a more than one loop, and you know it will become even clearer. So you will have inside this coil, the magnetic field is like that, and at the top you have the north pole, at the bottom you have the south pole. And I will write it without proof. If you have a current loop, which is a circle with a radius r, the magnetic field at the center is given by this equation. Now, don't confuse this with the other equation we had for straight wire. For the straight wire, the distance r is equal to mu0 I over 2 pi r. For a loop, at the center of the loop, the magnetic field is mu0 I over just 2r. They are not the same. That is for a straight long wire, and this is for a loop of wire carrying a current I. This r is the radius of this loop. And there, that small r is the distance from the straight wire to that point here. There is no pi there. There is a pi for the long straight wire. Here, there is no pi. You know, that is not the only difference. You should not confuse. What is this? This is the radius of the loop. What is this? The distance of the long straight wire to the point. So, you know, that is not the same thing. And there is a pi there. Here, there is no pi. What if you have more than one loop? You just have to multiply by n, the number of loops. Okay, now solenoid. What is a solenoid? Solenoid is a name given for when you take a wire and you curl, make several coils like this. So here coming out. This is, say, take a coil like that, cut it in the middle. So some part is out of the board, some part is behind the board. Okay. So here it is what I show in the dotted line is what is behind the board. The current is coming like that. When it comes out of the board, the current is going like that. So it is flowing in a certain direction. Okay, probably you can visualize now. So this kind of thing is called a solenoid. A loop, not just one loop, several loops, closely spaced, very close, tightly wound. And we call this device a solenoid. So you should know what a solenoid is. It has another name, electromagnet. Why? Why do you call it electromagnet? It's like a magnet now, right? A bar magnet with the south pole and the north pole. Whenever there is a current, it's a magnet. When the current is switched off, is it a magnet? No. So we call it electromagnet. Field lines inside the solenoids are nearly parallel, very closely spaced. And outside the solenoid is very weak, almost zero. Here we showing a solenoid. It looks almost like a bar magnet, right? The magnetic field line. So inside the solenoid also we will have magnetic field. It will be uniform magnetic field. Outside the solenoid will be a weak magnetic field. If you imagine an ideal solenoid mean very long, infinitely long solenoid, there will be zero magnetic field outside, only magnetic field will be inside, and it will be constant, uniform magnetic field. And the magnetic field inside a solenoid, because it is constant, and the value is given by this formula. So we have another formula now. Mu zero is the same constant. I is the current through the solenoid. What is small n here? Small n is not the same as the number of turns. It is number of turns per unit length, the length or the height of the solenoid. If you have several turns and this is the height of the solenoid, and you have how many n number of turns, the small n is total number of turns divided by the length of the solenoid. So we got another equation. This is for the magnetic field inside the solenoid, which is a constant everywhere inside, and it's given by this formula, mu zero small n into the current. This is the current. And where the small n is the number of turns, the capital N is the number of turns divided by the length of the solenoid. Can we obtain these results from Ampere's law? We can. Okay, probably it is in the next slide. But let me do this example question first. What's the time? 12:02. Okay, give me 5 minutes here. Right, it's a very easy question. We have a solenoid. This is the number of turns, and the length of the solenoid, that is small l. Find the magnitude of the magnetic field inside the solenoid when the current is I. So it's just a simple equation. B is equal to mu zero and I. Mu zero is 4 pi, excuse me, please pay attention. N is number of turns, small n is capital N divided by, so capital N is 100 divided by the length is 10 centimeter. 10 centimeter become divide by 100, 0.1. And I is 0.5. So just substitute and get the value of the magnetic field inside the solenoid. B. What is the momentum of a proton orbiting inside the solenoid? So we have the solenoid. The magnetic field will be like this. And there's a proton, positively charged particle, which is describing a circular path, because it has got a, this is a previous section topic. When we have a charged particle moving perpendicular to the magnetic field, it will describe a circle, and the radius of the circle is given by this. Radius of the circle is given by this. Radius is given. This is the momentum. It's a proton, that means we know the charge. Magnetic field is just found in A. Can you find the momentum? Yes, that's it. Okay. So the momentum is R, Q, B. R is given, Q is given, B is given. You substitute and get the answer.